Okay, and welcome to today's lesson for Chem Honors. And in today's lesson, we're going to look at what we call the heating and cooling curves, which is basically going to be another way of looking at exothermic and endothermic processes that are involved in heating and cooling and in freezing and vaporizing and everything all around those. And we're going to do that by first looking at a demonstration, which we would normally do in class, but I found a YouTube video. So make sure you go and watch that YouTube video linked here and also included in the assignment on the cooling of a material called stearic acid. Now, at room temperature, stearic acid is a solid, but if you take a test tube full of solid stearic acid and you put it in a beaker of boiling water, it will melt. Because, as we'll see, its boiling point, or melting point, is lower than the boiling point of water. The structure of stearic acid is shown to the right here, where each of those little vertices indicates a carbon atom that has either, well, at each vertex, the carbon atoms at each vertex would have 2 hydrogen atoms bonded. The last one here would have 3 hydrogen atoms bonded to it. So we get the full formula C18H35COOH. That COOH at the end here is the acid part of it. This is a weak acid, and we'll talk more about these in acids and bases. And an interesting thing about stearic acid, we've actually seen sodium stearate, where you take the H and you take that H off, and you put a sodium ion here because now we have a negative charge. Sodium stearate is one of the soaps that we saw way back in chapter 10, I think it was, when we looked at how soaps and detergents, how they work. Anyway, make sure you've watched that video, and then we'll come back here and take a look at what's going on. So from the video, we're going to see a few things going on. So in the video, we saw that initially the stearic acid was decreasing in temperature. And that's sort of like what's going on right around here, the decrease in temperature from the high temperature that it started at. Now, I'm continuing the line down below where the curve starts, or it starts to curve off, just because you're going to see a curve later on, or a plot later on, that's going to represent what is a theoretical kind of curve, whereas this is more a realistic kind of curve because of real world situations. So as the temperature starts to drop, you should have noticed that right about here, right where the curve starts to drop off, we have our first crystals. Starts to crystallize, and we get our first crystals. So that's where the first crystals were observed. Until you get to those first crystals, and you know what, maybe I should put that somewhere else. Let's put that over here, the crystals, so that I can point to this region and say, in this region, the stearic acid is all in the liquid phase. And as the temperature decreases, it stays in the liquid phase. It just gets colder as we're taking energy out. Now, on this plot, we have time on the x-axis, but one of the other things we can think about on the x-axis is, as we are moving along to the right, energy is being removed. Energy is coming, let's call it out, because it is an exothermic process. So energy is being removed as we move to the right. Okay, now, we'll come back to the solid region in a moment. When we got past that first curve, we saw that there is this plateau region. This plateau where the temperature was essentially staying constant. Where this temperature is staying constant, I wish it would stop doing that on me. Where the temperature is staying constant, no delta T, this constant temperature, this is where we have phase changes. And we'll see more about that in a few minutes. We'll talk a little bit more about that in a few minutes. So these phase changes, we're going to start off over here. We're going to start off 100% in the liquid phase. And as we move to the right, we're going to slowly get it to be to 100% in the solid phase. And everywhere along that line, so right about here, it would be about 50-50 solid and liquid. Then once we hit 100% solid, what happens is the temperature starts to drop again. So the temperature drops because this is now all in the solid phase, so all one phase. So we've now labeled the solid as well. From this curve, one of the things we're going to notice is that as we're going from the liquid to the solid, this is our freezing. And so the temperature at which the freezing takes place is the freezing point. And if you extrapolate over here, that comes out to be 68 degrees. The actual freezing point of stearic acid is 69 degrees. So we're off. It could be a slight measurement error. The thermometers, the temperature probes don't always work perfectly. Now, here's a concept that a lot of people struggle with. If you were to stop it halfway along, say stop at the 50-50 point, stop it right here, and start going back the other way, putting energy in, you would not change the temperature, but you would start to melt that 50% of the stearic acid that you have. And so it turns out that because of that, the freezing point and melting point are the same. And so the melting point of the stearic acid is also 68 degrees C. And that's because freezing is going from the liquid to the solid. Melting is going from the solid to the liquid. These are opposite processes, or essentially the same process, the same process in reverse. We just usually think of freezing as being cold because we put water into a really, really cold freezer to get it to freeze, but it will freeze. Its freezing point will happen at 0 degrees. And if you were to measure the temperature of the ice as it's forming, or the water as it's forming into ice, you would measure a constant temperature of 0 degrees. Now, what's going on in this diagram? How are we going to explain the different curves that are going on? Over the temperature range near the beginning, when the temperature decreases rapidly, the temperature decreases because the kinetic energy is going down. Remember, average kinetic energy, temperature is a measure of the average kinetic energy. And so what's happening is the particles are slowing down. Remember, kinetic energy is all about the speed. So the particles are slowing down and they're getting closer. They are getting slightly closer together because the density is going to go up, except for water. But that's not the important thing. They're getting slightly closer together. And since there's no phase change, the temperature goes down because all the energy released, this is an exothermic process, released goes into decreasing the temperature, decreasing that kinetic energy. Now, what happens when we get to freezing is that we switch. The reason the temperature reaches a plateau, it says it barely changes, and that might be noticeable on a very sensitive piece of equipment, but essentially the temperature is staying the same. So what's going on here is that delta T, that change in temperature, is equal to 0, so the kinetic energy must be constant. The average kinetic energy can't be changing. The delta KE, there's no change in kinetic energy. But we are removing energy, and the energy that's changing is that we're reducing the potential energy is being decreased. Now, the potential energy is due to the formation of, we'll call them, well, the formation of the intermolecular forces between the compound, between the molecules, due to the formation of the intermolecular forces as the particles get closer together. So a decrease in the potential energy also corresponds to a decrease in the distance between the particles. So we have formation of those intermolecular forces. And as they do so, it releases heat because it's exothermic that essentially keeps the temperature constant. So instead of having the temperature go down when you're removing the energy, the temperature stays constant because you're removing energy, but that energy then is being replenished as the exothermic process of freezing goes on. Now that continues all the way until you're done freezing. Then when you're done freezing, there's no more potential energy to remove. And then at the end, when the temperature decreases rapidly again, so the temperature is going to go down as the kinetic energy goes down. So we're decreasing the kinetic energy. Particles are slowing down. Now, in this case, because it's a solid, they're vibrating in place. They're vibrating more slowly. They're vibrating more slowly. And again, we get this delta T when there's no phase change. And as in letter A, all the released energy goes into decreasing that temperature. So this cooling curve it packs a lot of information into it. Now, let's look at number 5. Why is it, and I hinted it above, why does the temperature remain constant and doesn't continue to decrease even though we say it's cooling, the test tube was cooling in the air? So let's bulletize this, makes it a little easier. As the liquid goes to solid, what goes on is bonds, those IMFs, the intermolecular forces, form. By the way, the main intermolecular forces in stearic acid are going to be London dispersion forces. And you can see how having a nice long chain like it has of 18, actually there's 17 carbons, and then the carbon in the COOH. Oh, no, it does say 18 carbons, sorry. Gives you a large amount of LDFs. So the amount of energy is pretty big. Forming bonds is exothermic. And so the heat released is released by freezing. This argument also works if we talk about condensation as well. I want you to remember that down below when you're answering some of the questions. And this release of energy prevents the temperature from decreasing. So we maintain that temperature, and this is going to happen throughout all phase changes. So in number 6, if we were to turn around, I alluded to this earlier in talking about what happens if you were to stop in the middle of the freezing process. Suppose we get all the way down and we're frozen, and now we want to turn this around and heat up and put energy in. So on the x-axis, often you'll find on the x-axis with these heating and cooling curves, we'll see time on the x-axis, but you've got to remember that it's not just time. What's happening over the time is that energy is being, in this case, added in. So this would be like taking taking the system and putting it on a stove or putting it someplace where you can add energy. And if you add energy over a constant time, then you can figure out how much energy is being put in. So we'd get this heating curve. And this heating curve would look very similar to the cooling curve in reverse. We have the increase in temperature here. We've got the start of the melting and the end of the melting, and then we've got the increase in the temperature here. And the melting point is whatever temperature we have that is constant, as I said above. That would be the same temperature as the freezing point. So why does the temperature remain constant here as above? In the opposite argument, as we go from a solid to a liquid, bonds are broken. And breaking bonds is endothermic. You've got to put energy in to break apart the bonds. So endothermic, so heat is absorbed by melting. And we'll also see that happen. That says melting, not molting. Let me fix that. Melting. That also happens when we talk about boiling or vaporization. Boiling is just a certain form of vaporization. And the temperature stays constant. As the heat is used as the heat is used to break bonds. So the potential energy is going up rather than, and I need a little more room here, rather than increasing the temperature. That would be the kinetic energy changing. And I want you to picture a pot of water. Go back to boiling. A pot of water boiling on the stove. The energy that's going in, you're constantly putting energy in, but the temperature stays the same. And we've actually used hot water baths like this as well. All right, so this is the end of the notes for today. And on page 2, we have a few questions for you. Here's a generic looking heating curve. And like I said, this is a theoretical heating curve. So we get nice sharp breaks on the heating curve for solid, for where we get the transitions from delta T and kinetic energy changing to phase changes in the potential energy changing. So please go ahead and finish this up for homework, and we will see you next time in class.